Today we're going to examine what I suppose might at first sight appear to be a fairly easy problem. Suppose I have a triangle, and suppose I know what the coordinates of its vertices are. What I want to calculate, using those coordinates, is the area of this triangle. Well, that doesn't seem too difficult, does it? Surely all I have to do is to apply the formula for calculating the area of the triangle. I'm sure you know the one I mean. You measure the base, call it B, and then you drop a perpendicular from the opposite vertex to the base. Measure the height, that's h, and the area is a half times the base times the height, that's a half BH. But here's the snag. I can't apply that formula straight off if all I know are the coordinates of the vertices. It's not too difficult to work out the base length. In fact, I can calculate that exactly. It's just an application of Pythagoras' theorem. But the real problem comes when we try to calculate the height. See, I don't even know the coordinates of this point, where the perpendicular meets the base. But there are ways of manipulating this triangle to get round the difficulty, and that's what we're going to show you. And Bob is now going to explain the strategy that will apply to this problem.
Well, the way we're going to tackle this is by using an idea that you've encountered in the text. What we'll do is to use some transformations and their matrix forms to put the triangle in a particularly convenient place in relation to the axes, a position in which it'll be easy to calculate the area. I'll show you what I mean. Here's the triangle in the position you've already seen. Now let's move the triangle to this position. Now what have we got? Well, one of the vertices is now at the origin, and the side we originally called the base now lies along the x-axis. Now if we can determine the x-coordinate of this vertex, then we'll have the length of the base. But that's not all. Remember, we also require the perpendicular height. This length, from here to here. But that's now quite easy, provided we can calculate the y-coordinate of this vertex. So we now know what we want to do. But how can we get the triangle to this position from the original one? What transformations do we need? Well, let's do the movement in two stages. Firstly, let's get this vertex to the origin. We do this by applying a translation, like this. Now we want this edge to lie along the x-axis, and we can do that by applying a rotation.
So the sequence of transformations that we need is first a translation, and then a rotation. So now we know what transformations we're going to use. But we need the coordinates of the final positions of the vertices. And to calculate these, we'll need the matrix forms of the transformations to apply to the original coordinates, which are 1, 2, 3, 6, and 6, 5. And Bob's now going to show us how to do this.
So let's start with the translation. I want the matrix form of the translation that will take this point to the origin. Now, to translate this point to the origin, we have to subtract 1 from the x-coordinate and subtract 2 from the y-coordinate. And that's the same as applying this matrix transformation. Now let's find out what it does to all three vertices. So the vertex 1, 2 is now represented by this column matrix. And this obviously gives, after the translation, the column matrix 0, 0, as it should. Now let's save that result and do the same with the other vertices. Now I'll take the vertex at the top, that's 3, 6. The column matrix 3, 6 translates to 2, 4. Finally, the third vertex, 6, 5, translates to 5, 3. And this is what happens to the triangle under the translation. So that translation has got this vertex to the origin, and here's Mike to look at the next stage.
And the stage after the translation is the rotation. What we want to do now is to rotate the triangle from this position through this angle in this direction down to the x-axis. Well, that's going to involve the use of a rotation matrix. And here it is in its general form. Of course, what's missing from this is the angle through which we wish to rotate the triangle. But before we rush into things, there's one important point to remember. When we're talking about rotations, we need to specify two pieces of information. One is the magnitude of the angle through which we're going to rotate. The other one is the direction. Is the rotation in a clockwise or an anti-clockwise sense? Here, the magnitude of the angle is what I've called theta, and it's going to be easy to calculate what that is. But what about the direction? Well, it's clockwise. So I'm just going to have to be a little bit careful about what I put in this space here. It isn't just theta, because that would give me an anti-clockwise rotation through an angle of magnitude theta. What I need for a clockwise rotation is an angle minus theta. Here it is, the matrix for a clockwise rotation through an angle of magnitude theta. But it's much easier to work with sine and cos of theta rather than sine and cos of minus theta, as we've got here. So let's simplify these expressions in the matrix. Firstly, the cosine of a negative angle is exactly the same as the cosine of the corresponding positive angle. So cos minus theta is just cos theta. And the same goes for the other one too. But the sine of minus theta is the same as minus sine theta. And the remaining one is the negative of the one we've just done, so that gives us plus sine theta. So in principle, that's the matrix we need. And we apply it to the coordinates of the vertices we get after the translation. That will give us the coordinates of the vertices in their final position. Now the next stage is to find the values of sine theta and cos theta and enter them here. So let's now calculate these. To help us to do that, first of all, I'll put in a construction line here. Firstly, we need to know the length of the hypotenuse of this triangle. Well, by Pythagoras' theorem, the square of this length is equal to the sum of the squares of these lengths. This is the point 5, 3. So that's 5 squared plus 3 squared, 25 plus 9, which is 34. And so the length of the hypotenuse is root 34. So cos theta is this distance over this, which is 5 over root 34. And sine theta is this distance over this, which is 3 over root 34. So, now we know the entries in the rotation matrix. And that gives us the matrix form of the rotation.
Right, we're now at the point where we can pull the whole story together and calculate coordinates. Remember, we're dealing with a translation followed by a rotation, and we saw how we could apply the translation to the coordinates of the original triangle to move them to this position. And now we can apply the rotation to these new coordinates. But wait a minute, rather than do the calculation using two separate formulas, one for the translation and one for the rotation, can we find a single formula for the composite transformation and use that? Let's examine what we've done. We took our original vertex xy and applied the translation. Then we obtained the rotation matrix and we were ready to apply it to the resulting vertex to obtain a final position. So our composite matrix transformation is this formula. Now let's transform each of the vertices in turn using this formula. We'll begin with the point 1, 2. Doing the addition, we get the column vector 0, 0. Now we multiply them out, which yields a final result of 0, 0, which is a check that we've got the right transformation, since we wanted to transform this point to the origin. Now for the vertex 3, 6. Addition yields 2, 4, and multiplying out gives this, which simplifies to this, and finally to this, which corresponds to this point on the diagram. Well, that's 2 of our vertices transformed. Finally, 6, 5. Addition gives this, multiplying gives this, which simplifies, and finally comes to the column matrix 34 over root 34, 0, which corresponds to this point, which lies on the x-axis as we require. So under our composite transformation, we finish up with this triangle. Now we can work out the area. Here are the coordinates of the vertices, and the area is half times the length of the base times the height. Now the length of the base is simply the value of the x-coordinate of this vertex, and that's 34 over root 34. And the height is simply the value of this y-coordinate, and that's 14 over root 34. And this simplifies. The root 34s cancel with 34 to give 14 over 2, which is 7.
So having done our transformation, all we required were 2 values in order to calculate the area: the x-coordinate of this vertex and the y-coordinate of this one. By translating the triangle to the origin and rotating it, we simplified our representation of it considerably. And of course, this method can be used for any triangle in any position. The thing to remember is that an anti-clockwise rotation is a rotation through a positive angle. Clockwise rotation requires a negative angle in the rotation matrix. If we wanted to, we could use the same method to find a general formula for the area of a triangle in terms of the coordinates of its vertices. Well, we're not going to pursue that here. We're going to consider a different question, but one which is implicit in what we've been doing. Let's go back to our original triangle and think about the process again. How do we know that we've accurately retained the shape of the triangle under the transformation? Well, you'll probably say it was obvious from the pictures. But what we're trying to do is model the geometric transformations using matrix calculations. And how do we know that the matrix calculations accurately describe all the features of the geometric transformation? For example, in the geometric transformation, this line gets mapped to this line. But we must be sure that when we apply our matrix transformation formula to the coordinates of any old point on the original line, we do indeed obtain the coordinates of some point on this line.
So what I've got to do is to take a point on this line, transform it using this matrix transformation, and show that I get a point on this line. So what I'll do is take a point on this line with coordinates x, y, represent it by a column matrix, carry out this matrix calculation to get a new column matrix, which I'll call capital X, capital Y, and show that these are the coordinates of a point on this line. Well, what do I know? I know that this point lies on this line. So the coordinates of this point are connected by an equation, the equation of this line. Well, that's something we asked you to find out in the work before the program. And what you got was this: x plus 3y minus 21 equals 0. Now we can check that this is the right answer because first of all it has the right form for an equation of a straight line: number of x's, number of y's, number equals 0. And also, if I plug in the coordinates of this point, I get 3 plus 18 minus 21, which is 0, and similarly for this point. So it really is the equation of a straight line passing through these 2 points. Now what am I after? Well, I'd like to show that capital X and capital Y are the coordinates of a point on this line. So the first thing to do is to show that they're the coordinates of a point on a line. In other words, that capital X and capital Y satisfy an equation of the right sort to represent a straight line. Now how can I do that? Well, I shall have to bring in the transformation. Now capital X and capital Y are calculated from little x and little y by this matrix formula. So I can express capital X and capital Y in terms of little x and little y by working out this lot. So, to get capital X and capital Y, first of all, I must do this addition. Well, that's easy. That gives me x minus 1 and y minus 2. And then I must multiply the result by this matrix. So I have to multiply by the matrix 5 over root 34, 3 over root 34, minus 3 over root 34, 5 over root 34. Now if I do that, I get this times this. That's 5 times x minus 1 all over root 34, plus this times this. That's 3 times y minus 2 all over root 34. And on the bottom, I get this times this. That's minus 3 times x minus 1 over root 34, plus this times this. That's 5 times y minus 2 all over root 34. So capital X is that lot, and capital Y is that lot. And I can simplify these to get capital X as 5 times x over root 34 plus 3 times y over root 34 plus some numbers which collect together to give me minus 11 over root 34. So that's capital X. And for capital Y, I get minus 3 times x over root 34 plus 5 times y over root 34 and some numbers which collect up to give me minus 7 over root 34. So capital Y is that lot. Now all that is what I know, but what I want is the equation connecting capital X and capital Y. And how am I going to get that? Well, I know an equation connecting little x and little y. There it is. So if I solve these two equations to give me little x in terms of capital X and capital Y and little y in terms of capital X and capital Y, then I could take those expressions and substitute them in there, and that will give me an equation connecting capital X and capital Y. So the next stage is to solve these two equations to give little x and little y. All right, that's the next task. If I rearrange these by multiplying by root 34 in both cases and taking the constants over, I get the following. Now these are just a pair of simultaneous equations, and if you solve them, you'll get these expressions for little x and little y. Now, I wanted these in order to substitute them in the equation for this straight line. That is, in this equation, x plus 3y minus 21 equals 0. Now, if I do that substitution in this equation, I'll get the following. X plus 3y minus 21 equals 0, which is an equation connecting capital X and capital Y. And collecting up all the terms, I get this. Now let's just have a look at this. It's of the form number of x's, number of y's, the number equals 0. So it's the right form of equation to represent a straight line. So what have we shown? Well, we've shown that if we take the coordinates of any point on this line, they do indeed transform to a point whose coordinates, capital X and capital Y, satisfy the equation of a straight line. So all points on this line transform to points whose coordinates satisfy this straight line equation. Now, what straight line is it? Well, we know that that point transforms to that point, and that point transforms to that point. So this must be the equation of a straight line which goes through these 2 points. So this equation represents that straight line.
Let's just try and summarize what we've been doing. The theme that's been running through this program is of a correspondence between matrix calculations on the one hand, the kind of calculation that Bob's just been doing at the drawing board, for example, and on the other hand, geometrical transformations, such as the ones that we started off with. The ones we used, of course, were translations and also rotations. Now, the reason that this correspondence works is that the matrix algebra that we do models all the important geometrical properties of the transformations. For example, the geometrical transformation that we used preserves the property that points lying on a straight line remain on a straight line after transformation. And as we've just seen, the matrix transformation has exactly the same property. Now, this whole process is useful because it enables us to reduce geometrical problems to algebraic calculations. For example, a geometrical problem that we mentioned at the beginning is that of finding the foot of a perpendicular from a point to a straight line. And by using the kind of ideas that we've seen in this program, we could actually tackle that problem purely algebraically. Although we started off the program with the ability only to represent the transformations of individual points by our matrix calculations, the method that Bob used for his problem about the lines actually enabled him to describe the transformation of all the points on a line. In other words, he was able to find the equation of the transformed line, knowing the equation of the line he started off with. And this is an idea which we could extend to other sets of points which can be described by equations. And that's something that we'll be taking up later in the unit. And finally, let's just mention again this very useful idea we had at the beginning of the program, the idea for tackling geometrical problems using transformations. That idea is that you can move a figure from some general position into a convenient standard position where the problem then becomes easier to deal with.